Hello everyone, and many thanks for the organization committee, and especially for my colleague, for my friends Jean-Philippe and Nadim, and for everyone working in this for this maestro. Today I would like to share with you my experience with the Primo Monte Carlo code and to show you how to use it as a tool for dosimetry verification and as an independent quality assurance. This is my disclosure. Actually, I am working as a professor at UAG's at St. Joseph University at Lebanon in Beirut. And we have more than 20 years collaboration with Mount Lebanon Hospital and Hotel Dieu de France. At MLH, we have one Clinic IX, one Trubim STX, one Halcyon, and we have ARIA Eclipse 15.6. And we have element from Brain Lab for multiple brain metastasis, and we have SLS cranial and QPET, etc. At HDF, Hotel Dieu de France, we have two true beams, mirror, and we have ARIA Eclipse 15.6. Protocols like TRS or NCS that we use in radiation therapy, are they sufficient to ensure or to guarantee correct calculation dose of a patient dose? Not necessarily. Why? Because there are a lot of potential sources of error, like patient positioning or movement or modification in shape of internal organs. Plus, we need to check to verify TPS calculation, especially in an homogeneous medium. So for TPS, at least we can do a double calculation of double MU calculation with via an algorithm, but ideally is to use Monte Carlo algorithm. There are several Monte Carlo code like JM4, GATE, MCMP, etc. But they are often not free and requires good knowledge and theory. They are difficult to use and used only in research and thesis, dissertation, development, and medical application. And required adaptation or modification or creation of machine-specific phase space use. They are not applied to CT images of a patient. They are applied to sample phantoms without addressing other problems linked to radiotherapy. So what's the solution? In my opinion, is to use something like a Primo because it's fully Monte Carlo based Linux simulator. It gives a good estimation of the absorbed dose in phantom or CT. It could be an independent quality assurance tool. It's freely available. Primo can simulate variant machines, Electa as well. And by visiting the site of Primo project website, you can find a lot of information about the Primo's authors, installation, manual, article scientific, videos, tutorial, everything you need to learn about the Primo. There are several advantages of Primo. First, it's based on Monte Carlo code Penelope or dose planning method, which is 7 times faster. We can use MSC Millennium or Millennium High Definition. There is a possibility of calculation for rapid ArcVMAT and IMRT treatment. We can simulate FFF or FFF. There's a possibility of using cons for stereotactic. The graphic user interface is very simple and easy to use. There's a possibility to import CT scan plans and those via DICOM-RT. And the Primo allows comparison of calculated dose between Primo and Eclipse, and that via DVH and gamma index analysis, plus it's free. Primo is composed of PNeasy Linux or PNeasy. They are the main programs that contains different source models, variance reduction technique, creation of voxel geometry, PinoGeom, Pinovex, Penvox for geometry, Penelope and DPM for physics calculation. Here just it's, to show you the graphic interface of Primo, which is easy to use. You can do everything here. Primo simulation setup consists of 3 segments, S1, S2, and S3. S1, the upper part of the head of the Linux. To simulate S1, the primary beam parameters here can be edited or tuned to match between PDDs and the profile between Primo and Eclipse, and that is done via iterative process until a match between Primo and Eclipse is achieved. Another way is to adopt the phase space file PSF from my variant website to model the Linux head. In segment S2, we import field parameters, including treatment technique, beam weights, Gantt start and end, angles, collimator angle, couch, MLC, etc., etc. In segment S3, the Linux model is applied in patient and phantom geometry. Primo report dose on unit of electron volt by gram per simulated history. So a calibration factor is needed in Primo to convert electron volt per gram to gray. To do this, the measured dose at a point in reference condition, water phantom, field 10 by 10, SSD 100, is compared to dose provided or given by Primo. So the dose conversion factor F is proportional to dose measured under reference condition divided by the dose under the same setup given by Primo. I want to show you how to calibrate TrueBeam STX for 6FFF. The first thing is to import phase space for TrueBeam STX in 6FFF. After that, we can run a simulation on the reference condition SSD 100, field 10 by 10, and water phantom. When the simulation is carried out, we get a PDD here, and we look at the max, the value of dose, which is equal to 1.93 electron volt per gram. And this value is entered here as a reference dose, and we run again the simulation under the same reference condition, and you get again this PDD, and we look at the max, and you get we obtain a value of dose of 1 gray. To validate this calibration, this conversion factor, I calculate a PDD in Eclipse under reference condition 10 by 10 SSD 100 water phantom, and the plan is sent to Primo for simulation. And the simulation result give me a good agreement between Eclipse and the Primo. And red curve, this is the PDD from Eclipse, and the blue curve is the PDD obtained by Primo. We have a green curve here, represents the local dose difference in percentage, which is equal to 0 practically. And this agreement is very good with gamma index equal to 99% for criteria 1% and 1 millimeter. Primo workflow is summarized here by this flow chart. After project creation, we import or link phase space, and the city of a patient and the structure RS are imported via DICOM RT. We choose the mass density curve, which is equal, the same that one used by Eclipse and Acuros. The plan is imported via DICOM RT. We enter the factor of the conversion factor for calibration. We run the simulation, and finally we do an evaluation after importing of the dose, and we compare this with Monte Carlo Primo. Here's just an example of validation of a Primo for 6FFF TrueBeam STX for a field 15 by 15 SSD 100. After the simulation is finished, we have I compared the PDD from Eclipse to the PDD calculated by Primo. And here we see the profile at the 10 centimeter depth. And we have a comparison between Eclipse and the Primo. And the simulation show an excellent agreement with difference practically equal to 0 or less than 1%. The gamma index is 98.43 for criteria 1% and 1 millimeter. This is an interesting test called chair test. I calculated in Eclipse and simulated in Primo. Why this is interesting? Because with the profile A, we can confirm our MLC transmission, and the profile C between the two legs of the chair allows us to confirm our DLG dose leaf gap. And the profile B just corresponds to an homogeneous dose distribution. So I get an excellent comparison between Eclipse and the Primo, and that allows to verify our parameter, physics parameter like MLC transmission and DLG, corresponding DLG, dose leaf gap. I did the same thing for 6 MV. I get excellent result as well. I also for 10 megavolt. In order to test AAA and aqueous dose to water and aqueous dose to medium existing in Eclipse, so to validate this algorithm, an heterogeneous interface can help it. For example, I have this geometry: water, long, very low density, and water. And I calculate the PDD in Eclipse, and the plan is sent to Primo for simulation. So as you can see here, the simulation result show an excellent agreement between the Primo and aqueous dose to medium. The behavior of AAA and aqueous dose to water, they are similar. I have a difference around 5%. Another configuration is to test these algorithms with this geometry, water, bone, and water. And the simulation result show an excellent agreement between Monte Carlo and aqueous dose to medium. As well with the AAA, I have an excellent agreement, but not to aqueous dose to water. Another geometry here is water, bone, long, very low density, long, bone, long, very low density, bone, and long, low density, and water. So I calculate the PDD in Eclipse, I simulate that with the Primo, and the simulation result, an excellent agreement between a Primo Monte Carlo code and aqueous dose to medium, as well with AAA, but not to aqueous dose to water. For patient dosimetry verification, I tried several cases, and I will show you different cases here. The first one is a bladder, 3D conformal box technique with clinic IX. I have 15 MV and AAA. This dosimetry is done with Eclipse, and the plan is sent to Primo for simulation, and the results shows for dose distribution profile in axial, sagittal, and coronal. As you can see here, the result is very, very excellent. There's no difference between Eclipse and the Primo. A comparison of DVH, dose volume histogram, is shown here with the gamma index equal to 99.07 for 3% and 3 millimeter. And gamma analysis is complemented by a comparison of DVH using this formula PA percentage agreement. And the value of PA is given here also. As you can see, this is an excellent result. Here is an example of breast. So the gamma index is 99.08% for 3%, 3 millimeter as a criteria. Cholangiocarcinoma, it's a VMAT technique, rapid arc, 3 arcs, Trubium 6 FFF. So the comparison between Primo and Eclipse is shown here for dose distribution, profile dose distribution, and axial, sagittal, and coronal. And I get gamma index 99.9 for 3%, 3 millimeters. And for DVH, dose volume histogram, I get 99.62 for 2%, 2 millimeters. This is a case of a brain with two lesions, frontal and parietal. It's SFRT, isodose level 80%. It's VMAT, rapid arc, 3 arcs. As before, the comparison of dose profile distribution and axial, sagittal, coronal is shown here, and I get gamma index 100% for 3%, 3 millimeters. The DVH also is shown here. I get 99.78 for 2%, 2 millimeters. For SBRT bond D10, as before, as you can see, gamma index 99. The DVH also 99.85. And the last one case, I take the case provided by Mestro for study challenge. Pancreas, the dosimetry is done with our physicist. And I take their dosimetry and send to Primo for simulation. And I get an excellent result. For DVH also, I get 99.95% for 2% and 2 millimeters as a criteria. In conclusion, Primo code, I can tell you that the Primo code is a user-friendly interface for simulation of medical linear accelerators, which can be used as a tool for validation of TPS dose. It can be used as an accurate secondary dose verification and an effective tool to provide a potential independent quality assurance. And for future work, I would like to do a comparison between Primo and Element Brain Lab for multiple brain metastasis and SRS, and especially for small lesion for field less than 3 by 3. I would like also to do a validation of Primo Monte Carlo model of Halcyon. The phase space of Halcyon actually are available on bivariant, but we don't have the geometry, and we hope that that variant provide us the geometry of Halcyon in order to be able to do the simulation of Halcyon. Thank you so much.